Today I've got some very exciting news for you regarding some new products that we are announcing in our X-ray product line. You know, the advance of packaging, especially in 3D, more complex 3D structures, has really motivated customers to purchase the Exredia 500 series Versa XRN. In recent years, it has become the de facto standard for failure analysis for such complex advanced devices. Up until today, this has been the major product for us selling into packaging. But today I'm announcing that we are expanding our product line for advanced packaging, both development and failure analysis, by adding a brand new Versa unit called 600 series Versa XRN. Plus, we are also offering two new products, 800 Ultra XRN and the Context Micro CT. So building upon its predecessor, the 600 series Versa is the next generation Versa instrument. The Versa has been very useful for inspecting intact devices of various sizes at high resolution. Sizes such as individual packages, perhaps circuit boards, and even 300 millimeter wafers. It's very flexible in the type of samples that you're able to image with this instrument at high resolution. The versatility of this instrument to inspect and view such a variety of samples is one of the main reasons for its popularity for failure analysis. We are also introducing a new nanoscale XRN, which has resolution down to 50 nanometers. It is a nanoscale resolution for imaging ultra-fine pitch interconnects. Thirdly, we are also introducing a micro CT that is excellent for large field of view imaging for all sample types, and it provides high resolution, particularly for small sample types. And one unique aspect of the Context Micro CT is that in the field it may be upgradable to a Versa X-ray microscope. So we start with a source of X-rays over here, which pass through the sample and then are detected by the X-ray detector over here. And by rotating the sample, we acquire many 2D projections, very much like X-ray and then projection, and then turn the sample, another projection, and you all the way around, sometimes as much as 1,000 projections all the way around. So of course, these are 2D images. So the next step is to take all of these projections from all of these different perspectives, mathematically reconstruct and create a 3D volume, which example is shown here. This is the same process for CT scan at a hospital, only we apply it on a sub-micron scale. And one of the most valuable aspects of these 3D data sets is the ability to do virtual cross-sections. And that is what you see over here. This is a cross-section of this data set. This is not the same as a projection. This is a cross-section of this 3D data set. So I would like to summarize the Versa X-ray microscope, which has a very unique detector design. The detector is shown over here. Notice how it looks very much like an optical microscope. We call this technology X-ray microscopy because the detector is actually a microscope. And it has the advantage that it does not lose resolution as sample sizes change. And because of these reasons, it has been very popular with failure analysis labs. We have the Versas are installed in nearly 100 FA labs worldwide. A common application for the XRN systems is to do package failure analysis. Usually following the fault isolation step, the XRN is used to image those failure locations before going to physical failure analysis. And because you have an image of the defect, it helps you increase your success rate of accurately determining root cause of failures by having a picture of it before doing physical failure analysis. So a big advantage of having the 3D data set is being able to interact with it. You can look at cross sections very flexibly, in this case from side to side, but you can also look at it from top to bottom, from front to back. You can flexibly look at cross sections of this data set, as many orientations as you would like. This is very much more flexible when you do PFA. You make a cut and you only have one plane to examine. Now you can look at any plane in this data set. And this is the big attractive feature for failure analysis labs. Of course, not all X-ray is the same. For many years, 2D X-ray instruments have been a standard part of failure analysis and even production. With the advance of 3D architectures and complex 3D packages, it becomes harder to see what you need to see with 2D X-ray. For this 2.5D device, here is a 2D image, and here's the 3D image of about the same location. Similarly, here's a 2D image of the same location as this image on the same part. Clearly, there is a lot more information in the 3D image than is possible with 2D. So now that I've explained basics of how tomography works, how 3D compares to 2D, I would like to explain now what the difference is between the Versa X-ray microscope and a micro CT. As all of you may know, there's many micro CTs on the market. So this same explanation applies to virtually all of them. So we start with the tomography process. As I explained before, you image projections while rotating the sample. Now what happens with a conventional micro CT, if you look at resolution from high resolution to low resolution, so this is in microns, versus working distance. Working distance is the distance from the source to the center of sample rotation. What happens when samples get bigger? You must move them away from the source so you can rotate them fully without running into the source. For the case of micro CT, as working distance gets bigger, as samples get bigger, resolution goes down linearly because it is dependent on this equation. For the case of the Versa system, the architecture has unique detector. In fact, when you compare detectors, the detector for the Versa is a microscope. The detector for a micro CT is a flat panel detector. Because we use a microscope turret, this is where our resolution is gained by our microscope. Because of that, we are able to maintain with the Versa resolution even for larger samples that's very high, much higher than the case of micro CT. So the big difference between a micro CT and an X-ray microscope is that the Versa X-ray microscope maintains resolution regardless of working distance. Now, the other characteristic of a microscope is that you can zoom in to an intact sample. In this case, we looked at a smartphone and looked at several areas of the smartphone. We just saw a IC chip. Now we're looking at the lens element of a mobile phone, and also looking at the battery itself. And so you can zoom in to the sample. This is another characteristic of the Versa XRM. So as I mentioned earlier, the 600 series Versa is the next generation Versa, and it provides half micron spatial resolution with a 40 nanometer minimum voxel. And this is a nearly 30% improvement in our specification compared to the 500 series. The 500 series was 0.7. The 600 series is now 0.5 microns spatial resolution. The heart of the system is a high power source, a new source design. It provides up to 2 times higher throughput than the Exredia 500 series. Also, it maintains high resolution with excellent stability. By all the learning that we have gained from the 500 series has been built into this new source, and it maintains excellent stability and high resolution across the full energy and power range. Also, there's some ease of use improvements, including with the new source, it is very fast, activating very fast, and this improves the user's experience in using the tool. And like the 500 Versa, it does enable visualization of defects prior to physical failure analysis, guiding cross-section, mechanical cross-section, leading to improved FA success rate. In comparing the image quality versus the 5XX, the 6XX provides at least, if not better, image quality at up to 2 times faster acquisition rate. The example I'm showing is a reliability test. In this case, it is 30% faster than the 5XX. But in certain situations, the system goes up to 2x faster than the 5XX. This is the industry's only synchrotron-based nanoscale 3D X-ray microscope, and it delivers the highest possible resolution, 3D resolution from an X-ray instrument that is available on the market. It provides 2 modes of operation. One mode delivers 150 nanometer spatial resolution. The second mode delivers 50 nanometer spatial resolution. Similar to TEM, this instrument requires sample preparation, and it requires that a cylinder is extracted from the sample. In this case, it contains a micro bump here, and also some back end of line features, metallization features. But this sample is typically 100 microns in diameter and can be easily extracted in under 1 hour using a third-party laser sample preparation device. And one thing to point out, once the sample is prepared, the imaging is not destructive, non-invasive to the sample. And so it can be used for imaging ultrafine pitch interconnects and other ultrafine features, such as back end of line features, as you see on this image here, but also chip package interface type issues, may be imaged with the Ultra. And as I mentioned, this is a unique instrument. It's got a unique X-ray optics configuration that is similar to instruments that are used at synchrotron facilities. So it is a quite unique lab-based instrument. So to give you a feeling for a comparison, Versa versus Ultra, the Versa X-ray instrument images without requiring sample preparation, so the whole sample intact. It provides minimum half-micron spatial resolution, and it is the most versatile X-ray microscope for imaging localized defects within intact packages. The Ultra does require sample preparation, typically accomplished by a laser-based lift-out preparation. The sample volume remains intact and is protected from the environment and is imaged by either 150 or 50 nanometer spatial resolution. And it is unique for analyzing ultra-fine pitch, flip chip, and bumped connections. So this is a typical failure analysis workflow. It starts at the left side where you've confirmed electrically that something has failed and the sample is intact at this point. Then there's some elements of physical failure analysis which begin to be destructive to the part over to the right-hand side. So where does the Versa fit? Is by imaging intact devices and looking at internal interconnects before proceeding on the FA workflow. And then the Ultra is placed more so to the right because it requires sample preparation and analysis of back-end-of-line and chip package interconnect problems. So here is an application example from the Ultra. On the left side is the extracted region of interest, 100 micron cylinder. And in this case, we are examining the microbump. Here's the 3D data set that is produced by the Ultra. This is a 25 micron microbump, copper pillar, and the solder in between. By taking a virtual cross-section, you can see that here is an image, and you can even see the intrametallic, and you could begin to see Kirkendall voids here in this virtual cross-section. Before, it is pretty much required to use SEM to image and actually image intermetallics. With the Ultra, you could begin to see the intermetallics as you could see here in this virtual cross-section. You can also look at just the solder by itself, and that's what this is, and you can actually look at the roughness that's at the interface. So there's some flexible analyses you may accomplish with the Ultra, and you can visualize bump alignment and bond line stack-ups, solder shapes, extrusions, interfacial textures, intermetallic thicknesses, and so on, which enables you to localize, determine root cause of buried defects, do nano-level design and process optimization, also to help you with your simulation models, particularly in development. The context is a micro CT. It enables large field of view, 3D X-ray images for a variety of sizes, flexibility in sizes like the Versa, and it provides a minimum 0.95 spatial resolution with half-micron minimum voxel size with excellent image quality and contrast. It is using a high-speed 6 megapixel detector, a flat panel detector, as I described before, and it provides a large field of view with a 10x greater volume for the 3D data set as compared to the Versa XRM. The one advantage it has is you can field upgrade or field convert it to an X-ray microscope. Of course, like all micro CTs, the resolution will degrade as sample sizes get bigger. So high resolution is maintained for very small samples only. as samples get bigger, the resolution degrades, like all micro CTs. So here's an example from the context. This is a smartwatch, and with the context, you can image the entire smartwatch, as you see here. And to some level, you can actually zoom in as well by moving the watch closer to the source. You can get a higher magnification image, as you see here. You're just limited, you can move it no closer than to allow it to go and rotate in front of the source. All right, so to summarize, as we've heard earlier in the presentation, silicon scaling is slowing, and packaging, innovations in packaging is to help fill gaps in product performance and cost performance. As a result, devices are becoming more complex, more 3D in nature. Traditional construction and failure analysis techniques are not adequate for many of the advanced devices these days. And to address these requirements, ZEISS is expanding its packaging X-ray portfolio. And so, this is my last slide. So today, to summarize, we are introducing these 3 products. The 600 series Versa, the next generation of the Versa product line, which is the industry standard for failure analysis of complex packages. And we are expanding our portfolio, and we now offer the broadest portfolio of high-resolution X-ray instruments for advanced packaging by including the 800 ultra nanoscale resolution imaging for ultra-fine pitch interconnects, and the Context Micro CT, which provides a large field of view and high resolution for small samples.